Hi, I'm Guido Meardi and I'll be talking about MPEG 5 Part 2 LCVC, Low Complexity Enhancement Video Coding, the third MPEG video coding standard of 2020. In this presentation, I'll try to address three main topics. First of all, how LCVC is different from other coding standards. In particular, it's not a codec, it's a codec agnostic enhancer. Secondly, the types of performances that we can expect based on the independent evaluations performed in the past year. And third, how easy it is to implement it in practice and the types of use cases where we can expect faster traction over the next few months. First of all, why LCVC? Why would it be important? Well, the world demands video at a massive scale. We know it and it's everywhere. It's not just media. Higher and higher amount of video feeds at higher and higher resolution over wireless unreliable networks, sometimes with tight constraints of real time or even low latency. And also using battery-powered devices, sometimes not just at the decoding end, but also at the source. So all this puts a lot of pressure on the system and big requirements for compression efficiency, but also processing power efficiency. And LCVC can help with both. So how is LCVC different? First of all, it's not one more codec, but a codec agnostic enhancer. So LCVC enhances any codec by adding high definition details starting from a lower resolution video encoded with the enhanced codec. And by doing so, it enhances the compression capacity of the codec by making the compression efficiency as close as possible to its next generation, whatever that may be. And also by reducing the overall processing power requirements for serving a given resolution. The key design factors include a very simple low computational toolset, software-driven implementation by design, leveraging on available hardware acceleration, and also codec-agnostic design, immediately useful with old or current generation codecs and still useful tomorrow with next-generation codecs. These factors enable LCVC to rapidly enhance the quality and cost efficiency of all codec workflows via backward-compatible software add-on, and also simplify the transition from older generations of codecs to newer generation codecs by reducing the requirements and the costs to support a given resolution with the next generation codec. Sometimes, in order to explain the difference between LCVC and traditional codecs, I like to liken codecs to stars in a beautiful night sky. Sometimes we forget about it, but when we look at a star, we're actually looking into the past, because when we see a star, that light was actually emitted several years ago, sometimes very many years ago. And similarly, when we see a codec in operation, that codec may have been standardized several years ago because it takes so long to get the hardware acceleration in place, change all the devices, etc. In all this, LCVC is not another star, but it's a different entity. It's like a moon. A moon is not a star. It needs the light of another star to shine. But if it's light you're looking for in a dark night, it's quite shiny. And in particular, its light gets to you in 1.3 seconds. Out of analogy, LCVC is not a codec. It requires another codec to shine, but if it's efficiency that you're looking for, you can get it pretty quickly without having to wait for several years. So out of cosmic analogies, better compression typically comes at a cost. And over the generations of codec standards since the advent of digital video, we actually saw better and better compression, so the light blue bars going down at the cost of computational complexity going up. And the challenge of this is that the need for hardware acceleration means several years to go to mass adoption, duplicated workflows to upgrade the service, and also cost and sustainability issues for higher resolutions. LCVC redefined the trade-off by helping every codec on both computational efficiency and compression efficiency in different ways, because of course the less compression efficient a codec is, the more the benefits of LCVC will be in compression efficiency. The more efficient the codec, the more latest gen, the more the benefits of LCVC will be in computational complexity. So in both cases, actually acting on what needs more help. And most importantly, LCVC does this while maintaining deployability via software, including also software at application level or even HTML5 level in a reliable fashion. So how does it work? Well, it's a multi-layer scheme. So it uses the enhanced codec at a lower resolution, and by doing so, it makes it more efficient, both computationally and also in terms of coding efficiency. So Initially, the base codec creates lower resolution frames. Then an initial enhancement corrects the artifacts in the base. Then an adaptive nonlinear smart upsampler reconstructs the target resolution. This is something akin to a sort of super simple super resolution because it's encoder driven, adaptive and nonlinear, but it's also very simple from a computational standpoint. And lastly, further residual details are added to reconstruct the final frames, also leveraging on a temporal buffer for temporal correlation. The combination of this creates the advantage, and it's also leveraging the toolset of LCVC that you can see here in this chart. The most important part of this chart is not really what you see, but what you don't see. So you can see typical tools for a codec, but it's most important what you don't see. It's very simple. It's very few tools. Normally a modern codec would have tens of tools, while in this case there are very few. However, it's simple but not trivial because these tools are heavily nonlinear, adaptive, flexible, interlocked. And in addition, the LCVC format provides a lot of flexibility and extensibility for the future. So its performance will grow as codecs grow. And actually tools like custom quantization, custom upsampling, signal post-processing, non-normative user data to signal both technical and non-technical parameters will make LCVC better and better as time passes. When we talk about details, the tool set of LCVC makes it very efficient and sometimes I say lean and mean at encoding stuff like this. So when talking about details, it's sparse, highly detailed information like this one. Mostly impossible to infer for an upsampler because there is real information in details. And LCVC has tools like small transforms and other tools that are specifically aimed at encoding efficiently this stuff. There's a nice paper published this summer for SPIE. You can find it in lcvc.org in the resources section that compared the efficiency of LCVC at compressing details versus that of HM, so the test model for HEVC, when fed a layer of residuals like the one that you've seen before. What came out, not surprisingly, because LCVC was designed with this in mind, is that LCVC is more efficient than HEVC at compressing high-frequency details, but most importantly, it is more efficient despite almost 2 orders of magnitude of lower complexity. So, it's kind of this combination, this being very aimed at this, that makes it so efficient. Another question about details is, do we really need them? Couldn't we just make peace with sending lower resolution, and with the advent of more sophisticated upsampling techniques, even deep learning, AI-based supersampling, can't we just send low resolution video and then let upsampling do the trick? Well, in reality, we can't, because there's a lot of real information in details, and sophisticated upscalers can do a lot of things, but they cannot invent information that they don't know. And especially with small text, with logos, with things that are also important for monetization, it actually costs very little for LCVC to send the real information and send real fidelity, while it would be very difficult even for humans, let alone a deep learning technique or another technique, to infer those details. And here you can see an example with small fine print text. It's a magnified example. If you just downsample it and re-upsample it with Langshot, so without even compressing, so just perfect downsample source, it's very difficult even for a human to understand that that's an 8 or the R or the H. While instead it takes very limited bitrate and very limited complexity for LCVC to reconstruct a near perfect rendition of the text. Other tools of LCVC are also interesting, like encoder-driven adaptive post-processing, like adaptive dithering. You can see here how it can get rid pretty quickly and without consuming bitrate nasty artifacts like banding and blocking, especially jarring in dark scenes or with HDR. You see here on the left the same encode turning off dithering, and on the right turning it on. This is actually with gamma adjusted to 3.0 to enhance the effect. Actually, in real life, it would be a darker scene and the effect would be much more subtle. But essentially shows like how it can be used to eliminate banding and blocking effects. In terms of performance, I mentioned before the lcvc.org website. I would encourage anybody interested in performance evaluations to take a look at the resources section there. There have been a lot of evaluations performed on both test models and optimized implementations. I will give here a few flashes, but there's not nearly enough time to go through them. So, if you're interested by any means, please look there. In terms of test model results, the latest common test condition results show the gains provided by LCVC when enhancing JM, the test model for AVC H.264, and when enhancing HM, the test model for HEVC. In general, all the comparisons compare a codec used natively at full resolution versus the same codec enhanced with LCVC. And as you can see on the top left, the benefits are significant in the CTC conditions. Some questions were asked on what happens when you extend the bitrate range beyond the purpose of LCVC. LCVC is focused on providing benefits at bitrates that are typical of mass market video distribution. So one question was like, what happens when we go towards transparent quality, very high bitrates, so more typical of contribution, for instance. And you can see in the bottom right the results, which are pretty consistent. So we could safely say that LCVC works pretty well also at extended range. Most importantly, the results are confirmed with optimized implementation. So very often it takes years to see the same results as test model translated into practice because of the complexities of optimizing tools. In the case of LCVC, thanks to the low complexity toolset, the optimized implementations are showing already today results that are in line or actually even slightly better than the test model results. This assessment was actually performed by Janoser, editor of streaming media, on 33 sequences of 5 genres: esports, animation, movies, sports, and various. Results are very consistent with what we've shown before, so an average BD rate improvement of 42% in VMAF and 45% in subjective MOS. Most importantly, in this analysis, Janoser performed analysis on a lot of metrics and also using 2 formal MOS methodologies for subjective evaluations, both the ITU BT500 assessment, the one used at MPEG, and the Moscow State University crowdsourced Subjectify methodology with 5,509 viewers. And actually the results show that VMAF among the objective metrics is the one that shows the best correlation with ground truth formal MOS, although formal MOS typically shows even stronger gains. And in particular, what to bring home is that PSNR tends to be not a very good metric to assess LCVC enhanced encodes versus single layer native encodes. That's shown also in MPEG. It has reasons that are due to how MSE, mean square error, works, but they are a little bit beyond this presentation. Another question is how LCVC works in convex hull. So if it's possible to just lower the resolution and focus all the bitrate on a lower resolution, should we use LCVC or use just a lower resolution? Well, the results show that LCVC benefits are quite consistent also in a convex hull. This chart, for instance, shows a comparison of an ABR ladder going from 360p to 1080p. You see in red an X.264 ladder, and in blue an equivalent LCVC X.264 ladder. As you can see, the BD rate benefits are pretty in line with what we've seen before for comparisons at single resolution. Also, another question is how the benefits translate when we move from H.264, so less efficient codecs, to HEVC or even next generation codecs. And again, the results are pretty consistent. So here you see, for instance, the difference between X.264 very slow in purple with LCVC enhanced X.264 very slow orange, and you can see that the delta is pretty similar to what generated over X.265 very slow in brown by the red LCVC X.265 very slow. Another analysis did the same thing over a much broader test set of 136 clips, and again the results are pretty consistent with the median BD rate VMAF of 30.3% benefit. There are fewer tests conducted on AV1, VVC and EVC, but the preliminary results seem promising. For instance, AV1 with a 4x speed up, which is quite significant and important for AV1, still the benefits seem akin to 20-30%. These are preliminary and uncalibrated, so we expect them to improve with a bit of calibration. and there are some analysis being performed in these weeks, so we should see more coming soon. Similarly for VVC, again with the 4x speed up, some gains, about 7% on average in this example. Again, it's preliminary and calibrated, so hopefully with some calibration it could become double digit. But most importantly, despite a notable speed up, we are not losing compression efficiency, which is not what typically we would expect with such a speed up, but we are actually preserving it and, if anything, increasing it, which is a pretty big deal. Compression efficiency is always difficult to assess, but at least the speed is very simple to assess, and LCVC is very, very fast. This is true for test models, but in particular also for optimized implementations. For encoding, we can expect about a 2 to 2.5x speed up for H.264 AVC codecs, and even higher gains for more complex codecs, like a 3x for HEVC and up to 4x for AV1, EVC, and VVC. On the decoding side, despite LCVC being decoded in software thanks to the availability of SIMD pipelines, GPU processing, decoding of LCVC is actually hardware accelerated, and so LCVC enhanced decoding decodes with ballpark similar processing consumption and battery consumption as native hardware decoding, which makes it easy to deploy also to battery powered devices and low power devices. In order to show this a little bit, I would ask now Fabio to show a demonstration of how one would go about using LCVC, both with native libraries at application level or even HTML5 on a browser without plugin. So Fabio, can you please show us something?
LCVC is extremely easy to deploy as a software update. In this demonstration, I will show you how I can use LCVC within an application to enable encoding and decoding of LCVC enhanced streams, as well as add LCVC to an operating system to make those capabilities available to multiple applications on a single host. On my laptop, which is a standard Windows 10 machine, I've started encoding some content using an LCVC enabled FFmpeg build. It is a simple patch to FFmpeg that enables LCVC to enhance a number of different codec implementations, in this case H.264. While my content encodes, I'm going to install an MFT or Media Foundation Transforms, a Windows generic model for processing media data. This will add LCVC decoding capabilities to my Windows machine and all the apps that want to leverage it. In fact, at the end of the installation process, I can inspect my registry and find an LCVC MFT alongside those of other popular audio and video codecs. With this, my UWP or Universal Windows Platform Player app is able to open the file and decode the full HD resolution with the LCVC enhancement applied, here represented by an L+, the codec it enhances. As you can see, the full 1080p at 3 megabits per second is played back smoothly. For applications in which the installation of native libraries is not possible, such as in browsers, LCVC can be deployed simply as a scripted decoding function. This is quite unique. In this case, to demonstrate, I'm going to pick a URL from our cloud-based transcoding platform and simply paste it into the address bar of an HLS.js demo player that has been extended to support LCVC. In this case, you can see the same full HD 1080p content playing back smoothly at 30 frames per second in an unmodified Chrome browser without the need of any plugins or unnecessary installation. It is not only laptops and Windows-based systems that can so easily benefit from an LCVC enhancement. I will now plug in my Android-based phone and copy the same file that I just created onto one of its folders. On my handset, which is now about 2 years old, I have installed the vanilla version of Google Exoplayer that has been extended to add LCVC capabilities. These can be deployed as part of the app on any Android-capable system. I picked the file we just encoded, and here you can see it playing again in Full HD on my screen at 30 frames per second. Hopefully, this explains how easy it is to deploy LCVC as a software update to both applications and operating systems out there.
Thank you, Fabio. So LCVC is quite easy to deploy. Where can we expect it to be adopted more quickly in the next few months? In terms of use cases, LCVC is widely applicable, but of course it thrives whenever there are more constraints, whether it is higher and higher resolution, such as is the case for sports, esports, immersive video, or there are constraints of real-time processing, so live, or even ultra-low latency, such as cases like cloud gaming or video communication, and also delivering video over challenging networks or to a lot of concurrent users. So mobile entertainment, video anywhere there is a signal, or like big events that require a lot of concurrency. Also, intelligent media is a factor. Sometimes it's not just about video delivery, but it's also video analysis, where the availability of a multi-layer scheme can actually enable faster AI processing of both archives and live feeds. In general, LCVC can be very helpful for both greenfield deployments, where it allows greener deployments and also a next-gen type of quality with very low effort in terms of software integration, or brownfield deployments, where the benefit is material because of next-gen quality of experience benefits also for catch-all workflows going to old and new devices alike, plus the transcoding processing gains. Again, also here, the effort is relatively low. It's as easy as adding a new feature to an app. There's one more thing. We know that there's a little bit of an elephant in the room when we talk about adoption of a new codec. It's not just about technical prowess, but we've seen in recent years that the licensing terms of a codec standard are at least as important as anything else. LCVC has low complexity benefits also in that department, and there is a low complexity licensing model coming up very soon, and in particular it will be announced in a few weeks in December 2020, where the key design principles are really to be simple, to be inexpensive, to be faithful to the fact that LCVC is an enhancement, it's not a full-blown codec, and it can be deployed via software. So more on this very soon, but you can expect low complexity also on the licensing department from LCVC. And that's all. Thank you very much, and we remain open for any questions in the Q&A session.